Okay, so we're here reviewing. No one's watching yet. It looks like everything's working correctly, so that's good. Whoop. Spearmans R. I'm going to double check for you because when I think of Spearman, I think of Spearman's Rho, R-H-O, but I will double check the book. Here we go. Spearmans R, 311. Right, in some texts it's called Spearman's Rho, so that's how I've learned it. No, you don't have to worry about Spearman's R or Spearman's Rho. Essentially, so if you're watching and you're not sure what Spearman's R even is, it's another way of calculating Pearsons R when you can't calculate Pearsons R. But I will tell you that I wouldn't worry about it. So that's the answer. So Spearman's R is another way of calculating correlation when you can't use Pearson's R. It's just another way of doing it, but you shouldn't have to worry about it. A good question. Okay, so now there's a bunch of people here, so that's good. So please do put your questions in the chat if you have them, or email them to me. I'll pull out my email so I can see if there are questions coming in. I mean, conceptually, Spearman's R is going to be very, very similar to Pearson's R. So the things that are conceptually relevant for correlation are going to be conceptually relevant for both Spearman's R and Pearson's R. Spearman's R is just another calculation. So conceptually, it will be covered under Pearson's R. Good questions, though. Right. It's like I'm looking at the example of Spearman's R right now, and it's like how to do a correlation with ordinal rank data, like rank orders. So to put people in order of 1 to 10 in terms of best to worst, and then they do it again with like another category of people, and then do it 1 to 10, and then see if those ranks are correlated. That's something you don't have to worry about, but conceptually, the ideas of correlation still remain. Char, yes, I can. Pearson's R. I mean, good topic. We're still on correlation, so let's talk about Pearson's R. And I'll put in parentheses correlation because all of this, I mean, conceptually, Spearman's R falls underneath this as well. Okay, so this is when you want to see if like two IVs are related. Victoria, I can. Yes, I can. I can do those after this. So Pearsons R, and this will be a little bit of what you're asking for Pearsons R. So Pearsons R, you want to use it when you want to see if two IVs are related. So something like is height and weight related? Or I can even pull a question out of the book and see how they would ask a question like this. You could say something like is drug use, so like I don't know, like opioids, opioids. I don't know if that's spelled right. Is drug use related to alcohol use? So like, do these things go together, right? Does one go up when the other goes up, or does one go down when the other goes up, or do they both go down? That's when you want to use Pearsons R. That's when you're going to want to calculate a correlation. So that's like when you would do this. Next question is, how do you do it? So let's look at alcohol and drugs. So let's say I have some measures like, let's say beers per day. This is how many beers someone drinks per day. And the drug use is like, I don't know, pills per day. So I want to know if drinking beer, or the amount of beer drank, is correlated or related to the amount of pills that I take a day. So you'll get data in terms of beers per day, like this person drinks 3 beers and they take 4 pills a day. This person drinks 9 beers and they take 11 pills a day. This person, I don't know, drinks 1 beer a day and takes 0 pills. And this person drinks 3 beers a day and takes 7 pills a day. Right, so you get this raw data in both units. So you get this is in beers per day, this is in pills per day, and you can't really directly compare these because they're in different units. So the first thing you have to do is convert into a z-score. So these will typically be given to you. Remember what a z-score is back from like the first or second recitation. A z-score is telling you how far away from the mean a given value is in units of standard deviation. So if we took the average here and found 15 and 7 is 22 divided by 4, that's 5.5. Right, so the average pills per day is 5.5, and here is 16 divided by 4. Perfect, the mean is 4. Right? So for each one, then you'd have to calculate some standard deviation. Okay, you'd get this for each group. Then you'd have to calculate a z. So it'd be 3 minus 4 divided by the standard deviation. 9 minus 4 divided by the standard deviation. This is all, should be a review. It's from before the first exam. So you get a bunch of z-scores. Let's say this is negative 0.3. 9, we'll call this 1.5. This we'll call negative 2, and this we'll call negative 0.3 again, right? Because see, 3 is less than 4, so that's on the negative side of the distribution, and 9 is more than 4, so on the right-hand side of the distribution. All of this should make sense from before the first exam. So this is like negative 1, this is like positive 2, this is like negative 3, and this is I don't know, positive 1.5. So you get all these z-scores. And if you took like the practice questions, I think they're on Sakai, someone came to recitation today and showed me it, you'll get these z-scores. So here's where you need to know the formula. The formula for Pearsons R is the sum of zx times zy divided by the number of pairs of observations. Okay, so this would be like the given data that you would have. You would have some text about the question, then you'd have this given data, both the raw numbers and the z-scores. So now you have to calculate this. So the first thing you would do is you would take negative 0.3 times negative 1, and you would get positive 0.3. And then you would take 1.5 times 2, and you would get 3. Then you would do negative 2 times negative 3, and you would get 6. And here you would get negative 0.3 times positive 1.5, and you would get positive negative 0.5. About, right? So what this is zx times zy. So what I did was I multiplied this number, and then this number, and that number, and then this number, that number, and then that one, and that one. So we've done this part. We've done this part. Now we have to do this part. We add them all together. So 0.3 and 3 is 3.3, 9.3 minus 0.5. So 9.3 minus 0.5 is 8.8. So now we have the sum of zx times zy. Now the last thing we have to do is divide it by the number of pairs. We have 1, 2, 3, 4. We have 4 pairs, so we would take this, 8.8, and divide it by 4, and that would give us R. So now we just took this, and we divided by number of pairs, and we got 4. 8.8 divided by 4, so 2.2. Now, in this scenario, there should be a red flag. So in this scenario, it wouldn't ever work because R can only ever be between positive 1 and negative 1. So if you think about kind of where R can exist, you have positive 1, you have negative 1, and you have 0 right in the middle. Out here are positive correlations. Out here are negative correlations. And all the sign does is tell you about the direction of the relationship. The number itself, so like 0.3, 0.45, 0.8, 0.9, 1, negative 1, the number tells you how strong the relationship is, and the sign tells you the relationship. So what do I mean by that? So that's how you would calculate Pearsons R. You multiply the z-scores, you add them all together, and you divide by the number of pairs. Once you find R, you have to compare it to a critical value of R, which you would find in the critical value of R table in the back of the book using degrees of freedom, which in R is n minus 2, and number of pairs minus 2. And then you would accept or reject the null. Okay, so let's say we have height and weight. Now, you know, like, if you've ever met a baby, babies are short and they're not very heavy. So they're like down here. If you've met like a 10-year-old, they tend to be taller than babies and heavier than babies. So they're like here. And if you've met a fully grown adult, they are of varying heights and varying weights. So they're kind of all over the place. Lily, I'll get there. I'll take the questions in order, so yes. Okay, so if you just took people's heights and weights and you graphed them, you would get a relationship that looked like this. As 1 goes up, so as h goes up, w also goes up, right? So that's a positive correlation. You would expect an R value that's positive. And whatever the number is how strong the relationship is. but the sign of it being positive means that they're going up together. Or they could be going down together. As height goes down, weight goes down. That's also true. A negative correlation looks like this. Let's say this is your grade, and this is hours on internet. As hours on the internet go up from 0 to 100, your grade probably goes down, right? So if you spend no time on the internet, all you do is study, your grades are probably really good. And as you fill your meme folder with various memes, your grades might suffer. And as you only play video games on the internet and not go to class, your grades are going down even more. And so you can see here, you have a relationship like that. So as hours go up, grade goes down. So that's a negative R, a negative correlation. Again, the number, either it's 0.3, 0.5, 0.8, 0.9, whatever, the number corresponds to the strength of the relationship, how strong it is, and the sign corresponds to the relationship that exists between those two variables. So that's Pearsons R. So moving on from Pearsons R, I talked a little bit about the conceptual for that. Fischer Z. Fischer Z you don't have to worry too much about. The main thing about Fischer's Z is that it's a test to compare two correlations. So Fischer's Z is testing if two correlations are statistically different. Right, so let's say the correlation between, we'll call this weight, and we'll call this age. So as age goes up, weight goes up, right? And that would be like an R of 0.6. We could also do a correlation of weight and caloric intake. And it might be that this is like this, and this is an R of 0.88. Now, if I could only ask someone one question about their age or about their caloric intake, and I wanted to predict their weight, which would be better, right? Which correlation is stronger? What would give me a better opportunity to make an estimate of their weight? That's when you use Fischer Z. Fischer Z will test these two correlations against each other, kind of like a t-test. You test two things to tell if they're different. And then, depending on if the variance is low enough, then you can tell if they're different or not. Again, I would worry less about this, similar to Spearmans R, but know what it's for. It's for testing if two correlations are different from one another. And then conceptual ideas for paired samples t-test. It's very similar to independent samples t-test, except you have two groups that are related. So, I'm sorry, my nose is very itchy. So if you think about when you would use independent samples t-test, right? Independent samples t-test is when you don't have mu and you don't have sigma, but you do have two samples, and you want to tell if their means are different from one another. So you use the equation that looks like this. Right? So this is always the equation for t. Doesn't matter what type of t. If it's, this is both independent samples and paired samples. t equation is the same. The only difference is how you calculate the estimated standard of difference. And even then, it's not really different. So it's standard error of the mean for group 1 squared plus standard error of the mean for group 2 squared minus 2 times r times the standard error of the mean 1 times the standard error of the mean 2. Right? So really, this equation is not different for independent samples and paired samples. What's the main difference? The main difference is this part. And if r equals 0, like in an independent samples t-test, then the whole thing equals 0. And all of this equals 0, right? So when your groups are not related, when there's no correlation between your two samples, then you plug in 0 where r is, and that whole second half of the equation is 0. So you just get the estimated standard error of difference as we calculated for the first midterm, which was the square root of SEM1 squared plus SEM2 squared. Okay, so that's the only difference, is that extra bit when calculating the estimated standard error of difference. Now, a conceptual question that comes out of this is, why do you add that to the equation? So, like, why add this? Think about it for a moment. Why add, like, what's going to happen if you have a correlation here? If that value is something, then you're going to get some value, right? You're going to get SEM1 squared plus SEM2 squared minus some number, right? So you're making the sum of SEM1 squared plus SEM2 squared smaller, right? You're subtracting something from it. So you're taking some value, let's say it's 10, let's say this is 10, minus some number, minus 2, you're going to get 8, right? So if you compare the estimated standard error of difference in the independent samples t-test to the estimated standard error of difference in the paired samples t-test, assuming a correlation exists, there's a correlation there, you're going to wind up with a smaller estimated standard error of difference. And does that make sense? I hope that makes sense. So, like, for all other things equal, the estimated standard error of difference for the independent samples is going to be bigger. Whoops. Is going to be bigger than the estimated standard error of difference for the paired samples, because you're subtracting this, right? Because you're subtracting 2 times R times SEM1 times SEM2, right? When R is not 0, this is a number. That's this. So you're going to wind up making it smaller, which means, again, all things equal. So for your equation, t equals m1 minus m2 over estimated standard error of difference, right? It's just your t equation. When you make the estimated standard error of difference smaller, t is going to get bigger. And if t gets bigger, it's easier to find a significant difference. It's easier to reject the null hypothesis. So I guess all of that is just a prologue to say, why is that a thing in a paired samples t-test? Like, why does it work that way? Or why do you think it works that way? Like, why would you want to reduce the variance when you have a paired sample? And I'll tell you in a moment, once I figure out the best way to erase all of this. I'll put the important stuff back. Right, so here are the things that we know. T equals this minus this divided by this. We know that this equals this. So when R equals 0, then estimated SED equals this. That's what we learned for the first exam. When R equals 0, estimated standard error of difference equals that. And we'll call this estimated standard error of the difference independent samples. And when R is not 0, then it equals this, right? It equals this whole thing. And that's estimated standard error of the difference paired. And this is always smaller than that, because this is just subtraction. And the reason why this is, the whole reason why I'm going through this, the reason why is because when you have paired samples, then you have less variance, right? Like, if you have John and Mary, and John is he's a slow runner, and Mary is fast, and we take their average speed, it's going to be medium, right? This is all very qualitative. Now let's say we then give them lots of food, or we put, I don't know, we tie chains to their legs, or we make them carry heavy backpacks, something that will burden them, right? So we do that here. So here we add burden. And then we measure them again. And John is slower, and Mary is not as fast. So your average then is going to be, you know, slow. And the question is, does adding burden slow people's running speed? And the answer is yes, it does, because you go from medium to slow. But the reason why this is paired is because you're using John twice and you're using Mary twice, and they're similar to their previous measurement, right? John is still slow because he's just a slow runner. Mary is still faster than John because she's a faster runner, but she has slowed down, and so has John. They've both slowed down because of the burden, but they're both similar to themselves, right? The variance that exists here, so the v here, is the same as the v over here. It's not different. It's not bigger or smaller. It's the same. So, as opposed to independent samples, when all the people are unique, all the people bring their own running speed to the game. In this case, we have fewer kind of unknown speeds to worry about. We only have John's speed and Mary's speed, and whether or not that changes is a factor described by the burden. So when observations are paired, you have less variance because if we run you twice, Victoria, that's exactly right. Yes, it is easier to reject the null for a paired samples t-test than for an independent samples t-test. Exactly for this reason, because you make the estimated standard error of the difference smaller due to having a correlation. It's like you have one bag of variance, and that bag of variance goes with you for all the different measurements that you'll do. So like time point 1, time point 2. When you have two different groups, you now have two bags of variance you have to worry about and not just one. And so it's a little more difficult to do it like that than if you just have one quantity instead of two. Everything else about the paired samples t-test is the same as the independent samples t-test. So like if the two means get further apart, it would be easier to reject the null. If the estimated standard error of difference gets bigger or smaller, then that will change t accordingly. Everything we talked about before exam 1 for the independent samples t-test still exists. The only difference is it here in calculating the estimated standard error of difference and how the variance goes down in a paired samples t-test when you compare it to an independent samples t-test. I'm trying to think of other conceptual issues with the paired samples t-test. Here's a big one. So if you, I almost dropped my phone, sorry. If you calculate a Pearsons R, like let's say you want to compare two means, and you're unsure if those two groups are related to each other. So the first thing you have to do is do a correlation to compare the two groups of observations, and then you would do a paired samples t-test if they are correlated. If you fail to reject the null when calculating Pearsons R, then you would not do a paired samples t-test. That R, you haven't shown that there is a significant correlation between two groups. So if you don't find that, then you would do a regular independent samples t-test. And I'll write that down to try to put a fine point on it. So like just because you have an R doesn't mean you should do a paired samples t-test. That R has to be significant. You have to compare it to a critical value and accept or reject the null. And then if you reject the null, then you would move on. So if calculated R is below crit R threshold, 2 H's? I don't know. If it's below crit R threshold, I think it's only one. ESHOLD, whatever. you would fail to reject. And then for t-test, you would use R equals 0 or do the independent samples t-test, which are exactly the same. Right? If you plug in R equals 0 into the equation for the paired samples t-test, it would give you the same thing as the independent samples t-test. So if you fail to reject R, then don't use that R. Don't use a non-significant R in a paired samples t-test. Just a word of warning. Okay. And then Lily said, can we go over one-way and multi-ANOVA conceptually? I will do my best. Okay. So let's split this in half. Kind of. We'll call this one way. And we'll call this factorial. Okay. The really short answer is they're very, very similar. So the big thing in a one-way ANOVA is that there is one independent variable and one dependent variable. In the factorial ANOVA, there is two or more IVs, one DV. Here, there's only ever one F-test. For a factorial ANOVA, there is a one F-test per IV plus interactions. And I'll go through that a little more in a moment. So that's like the difference between the two. Both of them could use, so both of them might need two keys. Whoops. K, E, might need two keys HSD, depending on levels. So this is just kind of like an overview of what they are. The difference between them is just the number of IVs you have. For the test and for us doing this material in class, in the factorial ANOVA, you'll only ever have two IVs. Though, if you go into psychology or statistics or whatever, data science, whatever you're doing, factorial ANOVA, you could have a million IVs. But it gets exponentially hard to do it on paper over two. So we only do two. Okay, so conceptually, let's go through what the ANOVA is doing. Okay. So right? Analysis, so it's AN analysis of variance. And I make that clear for a reason. So let's say we want to know if School grade predicts weight. These should all be the same height, so I'll just fix that. Sorry. So these all should look the same. The drawing is not great, but let's say that this is first graders, this is fifth, this is sixth, and this is 10th. So we have first graders, fifth graders, sixth graders, and 10th graders. And this is the frequency, right? So this is just how many people. So number of people. Frequency. Whoop. I'm dragging things away. Okay. So you can't do a t-test in this because you have more than 2 groups. You have 4 groups. But you still want to know if grade affects weight. So what do you do? So we know that the equation for the ANOVA is called F, and that's the mean square between divided by the mean square within. And what those are has to do with sum of squares. So it's like sum of squares between divided by degrees of freedom between, and the sum of squares within divided by degrees of freedom within. So the measures of variance here are the sums of squares between and within. Now remember, the test is called analysis of variance. So looking for the measures of variance are very important. The mean square within and the mean square between, these are just a modified version of these, right? It's just the sum of square between put into context of its degrees of freedom, and the mean square within is just the sums of squares within put into context of its degrees of freedom. So the sums of squares are really the name of the game. They're what's driving the whole thing. Now, what are they? And that's a good question. So you know here we have a mean, right? And here we have a mean, and here we have a mean, and here we have a mean. Right? This is the mean weight for these different grades. So like the mean weight for first graders could be 50 pounds. And the mean weight for fifth graders might be, I don't know, 100 pounds. And the mean weight for sixth graders might be 110 pounds. And the mean weight for 10th graders might be 160 pounds. Right? So that's just the average. So you take all the first graders, you average them together, and you get some number, 50. And you do that for each group. Now, each grade is going to have some variance, right? Something that we call the standard deviation. Some level of spread. So like not every first grader weighs 50 pounds. Some might be 40, some might be 55, some might be exactly 50. It varies, right? And that number is, so the average from any given point within a group, wink wink, to the mean is designated as the sums of squares within. And you only have one of these for a whole ANOVA question. You might say, well, I have 4 distributions. Shouldn't I have 4 sums of squares within? It's also a great question. And the answer is, an assumption of the ANOVA is that all of these distributions are exactly the same shape, which is why I wanted to redraw that one that I drew all crazy. They should all be exactly the same shape, and they all share the same variance. So the sums of squares within calculated for first graders should be the same for 5th graders and 6th graders and 10th graders. So that's the variance within a group. Sums of squares within is the variance within the level of your IV. So within first graders, within 5th graders. Okay, so that's one half of the puzzle. The other half is sums of squares between. So I want you to imagine if you took all of these different people, first graders, fifth graders, sixth graders, 10th graders, and you average them all together. So 150, 260, 420. 420 divided by however many people you have. So 420, we have 4 means. 420 divided by 4 is, what, 105? Yeah, 105. Okay. So here we have the grand mean. And that's 105. Because that's the average of the 4 averages, right? So now, if I was to plot all of these on a distribution, I would get 105 as the average. Well, like any good distribution, you can describe it in terms of its center point and its variance and its spread. And so the spread from like any point, so like from here to here, from here to here, from here to here, or from here to here, that is described by the sum of squares between. So that's described by how far away is the average mean, what's the average distance from any given level mean to the grand mean. That's sum of squares between, which is represented in mean square between. So the whole idea of ANOVA is to say which groups are different, right? So at a given amount of sum of squares between, at a given fatness or skinniness of your individual level distributions, you want them to be spread out far enough that you can tell them apart. So you want sums of square between, what you want is this to be big, given your sums of square within. Right, that's what this is. You know that a big F, like an F of 10 or 20 or 30, is typically a significant finding. It's typically significantly different. And what that's saying, if you have an F of 10, it's saying that your mean square between is 10 times bigger than your mean square within. That's what the fraction is telling you. If you had 10 over 1, which is the fraction, right? 10 over 1, 10 is 10 times bigger than 1. Or 20 over 2, 20 is 10 times bigger than 2. So you want your means to be spread out from each other, and you'll need them to be even more spread out the fatter your distributions are. So the bigger your sum of squares within is, you'll need them a bigger sum of squares between. You want your sum of squares between to be bigger proportionally to your sum of squares within, or relatively, I should say, relatively to your sum of squares within. So that's and the F will tell you, like in this scenario with these 4 grades, F will be big enough to say there is some difference between means. Somewhere there's a difference between means. And you say, okay, well, where's the difference? And that's when you have to use 2 keys. I'll erase some of this. So 2 keys on a significant difference is saying the minimum distance two means have to be apart to be considered different. So what that number means is that your level means have to be at least that far apart for you to say there's a difference between these two levels. So in this case, in this example, let's say we calculate a Tukey's HSD of 30. And that's in pounds, LBS. So what that says is that your level means have to be at least 30 pounds apart for you to say that there's a difference in weight as you change levels. So here, 50 to 100, so we go from 50 to 100, the difference is 50 pounds. The minimum that I need to pass is 30 pounds. So here, oh God, it's going to mirror. I want to get rid of this. Go over there. Okay. So here, I would say they're different. Weight goes up from first grade to fifth grade. From fifth to sixth, that's only 10 pounds. 10 pounds is less than 30 pounds. So I can't tell if weight goes up between 5th and 6th grade. The difference here is also 50 pounds. And that's more than 30, so I can say these are different. And then I know 50 to 160 is 110 pounds. That's more than 30, so these are different too. And then 50 is obvious, it's 60 away from 110. So those are also different. So now I've found a significant F. I've said there is a difference in weight depending on the level of grade you're in. That's what F tells you. And then you have to calculate Tukey's HSD to figure out how far do the means have to be in order to consider them different. In this made-up scenario, we said 30 pounds. And so we can say weight probably increases between 1st and 5th grades. 1st and 6th grade and 1st and 10th grade. Weight also probably increases between 5th and 6th grade and 10th grade, though weight probably doesn't differ between 5th and 6th grades. Or that's how I would say it. Weight is probably not different between 5th and 6th grades. So that's kind of what we're doing with ANOVA. We are comparing multiple groups, and then we are, if there's 3 or more, trying to determine which groups are different from others after we accept or reject the null. You can only do a Tukey's after you reject the null for that variable that has 3 or more levels. If it has 2 levels, you don't need to do Tukey's because the F will give you enough information. The F says there's some difference between groups, and you only have 2 groups, so those 2 groups must be different. You can't have a difference with one group, and if there's 3 or more, there could be overlap. So with 2, it's like a special case. The F is gives you enough information for you to not have to do Tukey's. And the one way and the multi and the factorial ANOVA are like the same conceptually. The only difference is that the factorial ANOVA, you have multiple IVs. So let's say here, one IV was grade. The other IV could be gender. So does weight change? Is weight affected by grade of school and gender? You would do this for weight. You do it again for gender, and then you would do an interaction between weight and gender. So you would do 3 different Fs, and then do the same thing. If it has more than 3 levels, do Tukey's, and then write some sort of concluding sentence. Okay, so any other final questions? We have about 5 minutes left. And if you maybe come up with a question later on or feel like I didn't answer your question fully, there are still 2 other reviews online from the last 2 semesters for this exam. So if you go to my website, it's there. I'll leave a link. I'll put a link here in the chat, actually. Maybe not. So if there's more stuff, or you need maybe more prompting, or maybe someone asked a question better, or I explained it better in a previous semester, there's more stuff there too. So be sure to check it out. But we have a few more minutes, so if you have more questions, I have no problem going over them. No problem, Victoria. I'm trying to just think of, I mean, that's pretty much it, right? Correlation, paired samples t-test, and both types of ANOVA, one way and factorial. 2 keys HSD, things like that. Fischer Z is how you tell if a correlation is different from another correlation. Spearmans R or Spearmans Rho is another way of calculating correlation with different types of data. So really don't have to worry about that. Like, think about the data types you do need for each different type of test. Chinwei. So not on the test. Like, you wouldn't have to do it manually. There could be a conceptual question about that. Like, if you had a, let's say you have, so the short answer is you won't have to calculate more than 3 Fs in a given question on the computational exam. Like, you wouldn't have to sit there and do that. But you should know how many Fs you would need for a given setup of an ANOVA. So like, you have a 2 by 3 by 4 ANOVA. How many Fs? So how many F tests would you need if your setup was a 2 by 3 by 4 ANOVA? So this would be a factorial ANOVA, right? That's, see, it would be a factorial ANOVA. That's the question. And now I'll show you the, or I guess I'll try to write it on the same page. Oh, I know how to do this. I can highlight this and then move it like that. There we go. Oh. So that's our setup, right? This is an IV with 2 levels. This is an IV with 3 levels. This is an IV with 4 levels. So each value corresponds to an independent variable, and the value of that number is how many levels it has. So in this case, you would need an F just for that IV, an F just for that IV, an F for just that IV, 3, an F for this interaction, an F for this interaction, an F for this interaction, and an F for all three. So for a 2 by 3 by 4, you would need 7 F-tests. Right, so all three main effects plus 4 interactions. So remember, a main effect is just the independent variable by itself. So like just the effect of that one independent variable. And the interactions are the two or more independent variables together. So like just weight, just height, just age are main effects. And then the interaction of height and weight, the interaction of weight and age, the interaction of height and age, and the three-way interaction of height, weight, and age. So that would be like all the different permutations you could make. You would need 7 F-tests if you had a 3 IV ANOVA. Note how the number of F-tests does not matter on the levels that you have. It doesn't matter if it was a 99 by 99 by 99 ANOVA, it would still be 7 F-tests, because the levels are only telling you how many different groups are within that IV. So at the end, you'd have to do group mean comparisons, like with Tukey's HSD, comparing all those different groups. So just think about that. Okay, so we're out of time, unfortunately. I will be holding more office hours tomorrow from 11 to 1. My office is Tillet 429. There's an elevator in the building, so take it, or the stairs. Tomorrow, 11 to 1. And then we're also having like an extra optional recitation next Wednesday at our normal class time. So if you're in section 1, it's at 10:20. If you're in section 2, it's at noon. And then that's it. If none of those times work, if you really have a burning question and you need to get a hold of me, shoot me an email and we can figure out a time to talk, or we can just talk over email. And then that's it. So good luck studying. If I see you tomorrow, I'll see you tomorrow. And if not, I'll see you at the test on Tuesday. And I hope you have a good night. Thank you so much.